Welcome to the deep dive. Today we're cutting right to the chase on AI reasoning. We're looking at a new dataset from NVIDIA Nemotron-Math, and it claims to provide, well, a kind of shortcut to top-tier performance in really complex math problems.
It's a fascinating area because you have to understand the current barrier first. Mathematical problem solving is just incredibly tough for these large language models.
Right, it's not just about getting the answer.
Exactly. It needs multi-step logic, long context understanding. And the data sets we've been using, honestly, they often lead to what you could call monotone training,
Monotone, meaning what exactly?
meaning they all have these very uniform solution styles, and they focus way too much on formal competition-style problems.
And that just falls apart in the real world.
It fails completely when the model sees a messy real-world query.
Okay, so let's unpack how Nemotron-Math is trying to fix this. It's combining rich diversity with powerful long context supervision.
Right. They've generated 7.5 million training examples. They call them long-form solution traces.
What exactly is a trace for those of us listening?
Think of it like the model's entire scratch pad. It's not just the final answer.
Right.
It's every single step, every thought, every calculation that got it there. That level of detail is what you need to actually teach reasoning.
And to build that, they're pulling from very different worlds.
Totally. It's the structure of competition math meeting the absolute messiness of the real world. You got the AOPS source, that's art of problem solving.
Okay, so that's the clean, structured stuff.
Precisely. 85,000 curated problems.
Yeah.
But then you have the Stack Exchange math source.
Which is not so clean.
Not at all. 262,000 community-driven questions, often college level, sometimes even research-oriented. And that's what gives it robustness on benchmarks that test real-world ambiguity.
So for the solutions themselves, they use the GPTOS 120B model. But the generation process here seems critical.
Oh, it's everything. They explicitly control the reasoning style, so they generated solutions in 3 modes, high, medium, and low.
To get different paths to the same answer.
Yes, and crucially, they tracked if the reasoning used Python, what they call tool-integrated reasoning, or TIR.
And this TIR seems to be the secret sauce. I'm looking at these results. 100% accuracy on AIM benchmarks.
I know. AIM is notoriously difficult. And the top results, those perfect scores on AME 2024 and 2025, were all achieved using that high reasoning mode with Python TIR.
So what does that mage at 16 accuracy figure mean for us?
It means they ran the model 16 times on a problem, and the majority of those runs got the right answer. It shows the performance is repeatable, it's robust.
And it confirms that tools are not just an add-on.
They're essential. Absolutely essential for cutting-edge performance.
Okay, so if these traces are so detailed and they include code, they must be huge. We're talking up to 128,000 tokens.
Massive.
How on earth do you train on that efficiently? This is where it gets really interesting for anyone in the space.
Well, that's the problem, right? Efficiency. If 80% of your data only needs, say, 32,000 tokens, but you're training every single sample at the max 128K?
You're just wasting compute. It's like paying rent on 4 houses when you only live in one.
Exactly. So they introduced what they call a sequential bucketed training strategy.
It sounds complex, but it's basically just starting with shorter lessons and getting progressively harder.
Right. That's a great way to put it. They group the data by length, 16K, then 32K, and so on, all the way up to 128K, and they optimize the whole setup for each stage.
And the payoff.
It's huge.
Right.
Training throughput improves by 2 to 3 times. And you only get a tiny, maybe 1 to 3% drop in final accuracy. It makes these ultra-long contexts actually affordable.
So to put it all together for you listening, Nemotron-Math's breakthrough isn't just about harder problems.
Yeah.
It's about synthesizing diversity, tool use, and efficiency to create better, more scalable training data.
That's the core insight. The future of AI reasoning isn't just more data. It's synthesizing varied data, from structured competitions to messy real-world questions, and teaching models how to use tools effectively.
Indeed. Which leaves us with a final thought to mull over. If LLMs can now get perfect scores on advanced math competitions using external tools, what's the next real benchmark for human-level reasoning that AI will try to master?